This is Mr. Smith here. This is section 8.2. We're looking at rational functions. So to start us off, we need to know what we mean when we say rational function. A rational function is a fraction of polynomials. Okay? That means in this chapter we're going to be dealing with fractions, everyone's favorite. Moreover, these fractions are going to have variables on the bottom. So here, for instance, is a fraction or a rational function we took a look at in section 8.1. Recall 8.1, all we talked about was direct variation and indirect variation. It's not really a whole lot more to that idea. But here, I see there's a variable in the bottom of this fraction, a over x. That means there's going to be a domain restriction. Right? The domain is going to be limited. Okay. But any function in the form of p over q, where p and q are polynomials. Remember that a polynomial is something like a cubic or a quadratic or a quartic. Y equals 5x squared plus 7x plus 9. That's a polynomial. And we're going to put a polynomial in the numerator. We'll put a polynomial in the denominator. Okay. And so here is our parent function. All rational functions are structured around this parent function. So the idea of transformations, we're gonna be talking about transformations. But here's our parent function. Notice there's two asymptotes. We have a horizontal asymptote here, which is the x-axis, and we have a vertical asymptote here, which is the y-axis. When we do our transformations, those asymptotes are going to move with our transformations. Okay. So the asymptotes do get transformed. And in this graph, y equals 1 over x. In this graph, y equals 1 over x, the domain goes from negative infinity to 0, but not including 0. And from 0 to infinity, not including 0. What we're saying is, look, I can't plug 0 in because it's going to make the denominator 0. We're not allowed to have 0 in the denominator. Okay. The range, in this case, is also going to be from negative infinity to 0 and from 0 to infinity. Okay. Remember, range talks about the y values. And it's going to be pretty easy in this section, in section 8.2, because all you'll have to do is look at where the asymptotes are, and that'll tell you about the domain of range. So as I come across the x's talking about domain, I look for the graph, and I see, look, the graph is here, the graph is here. But once I get here, there is no part of the graph either above me or below me, which means that x can't be 0. Again, you can look into the function and say, well, I can't plug in 0 here, because that's going to put 0 on the bottom of a fraction. We're not allowed to have 0 on the bottom of a fraction. Okay. So here we're going to graph the function y equals 4 over x. This is going to have the same domain and range as the parent function. It's going to have the same asymptotes. Notice this, any function of the form a over x has the exact same asymptotes, domain, and range as this function. Okay, so that means we're going to get an asymptote here. We're going to get a vertical asymptote here. And now I get this very unique characteristic shape. But so the characteristic shape is going to be like this, right? And we're going to have two pieces. And to fill out how those pieces look, I'm just going to pick a couple x values. So if I plug in 4, I get 1. If I plug in 2, I get 2. If I plug in negative 4, I get negative 1. If I plug in negative 2, I get negative 2. So 2, 2, negative 2, 2, 4, 1, negative 4, 1. And so the graph of this guy looks like this and this. The shape has a name. It's called a hyperbola. Hyperbola. The two pieces are called branches. So we call these each branches. and this is a rational function. Okay, your graphing calculators will graph these. If we want to talk about the domain and range, the domain here is all real numbers except 0. And the range is also the same. So y equals a real number, but y does not equal 0. Okay. So now let's build on this, right? So this is our basic, this is our parent function. Sorry, this is our parent function. This is a slightly modified version. We won't give it any name of how it's transformed. We'll just say it's slightly modified. But we can talk more about transforming these graphs. Okay? And so in this format, I see y equals a over x minus h plus k. The k value here is our vertical shift. So it's going to take the entire graph, including the asymptote, and shift it up, k units. And the minus h, that's our horizontal asymptote. That's our horizontal shift. Excuse me, that's our horizontal shift. And it's going to move h units the opposite direction. So in this case, it's going to move h units to the right. And that's going to shift our vertical asymptote. Okay, so you can see the vertical asymptote started on the y-axis, and it shifted out h units. And this horizontal asymptote started on the x-axis, but shifted up vertically k units, which is exactly what we'd expect based on our knowledge of transformations. Notice we're not going to talk about a as a stretching factor. We don't want to talk about a as any stretch. Don't talk to me about stretching. So let's take a look at this function. We're going to graph this using our knowledge of transformations. But I want to modify the problem and make it a plus 6 to begin with. So we're going to start off as plus 6. And so here we go. The first thing is this plus 2 is a vertical shift. So that's going to move our asymptote on the x-axis up 2 units. So that gives us a new horizontal asymptote there. The plus 3 gives us a horizontal shift, 3 units to the left. So that's going to take the vertical asymptote that was on the y-axis. It's going to move it over 3 units. Okay. And so there are our asymptotes. If you want to, at this point, we can also talk about domain and range, right? Domain, x is a real number, but x can't equal, right, -3. X cannot equal -3. And you can either look at where the vertical asymptote is to help you, or you can look at this fact and look at the denominator and say, look, if I plug in -3, I get something that's undefined, because -3 plus 3 is 0. I'm not allowed to have 0 on the bottom of a fraction. And that thought process is going to be very important for you in this chapter. You are going to need to be able to look at the bottom of a fraction and say what value x cannot be. In this case, x cannot be -3. If we want to talk about the range, y is a real number, but y cannot be. And now we look at where the horizontal asymptote is, and here I see it's at 2. Y cannot equal 2. All right, now the only thing we need to do to be able to graph this is XY table. And let's pick some x values. Let's pick smart x values. If I pick an x value of 4, I get 6 over 7. That's not very nice. I don't want to do fractions if I don't have to. But if I pick an x value of 3, I get 6 over 6, which is 1, plus 2 is 3. If I pick an x value of 0. I get 6 over 3, which is 2, plus 2 is 4. So 0, 4 is there. 3, 3 is here. And so this is going to look something like this. Again, this piece will be symmetric, so however this one looks, this one will look the same. You can also pick some values to do this. So if we pick, for instance, negative 6. Negative 6 divided by negative 3 is negative 2, plus 2 is 0. So negative 6, 0. So 2, 4, 6. So that goes there. If we pick a value like negative 4, negative 4 plus 3 is negative 1. 6 divided by negative 1 is negative 6. Plus 2 is negative 4. So negative 4, 4. So let's see, there's 0, 2, 4. And so it gives us a graph that does something like this. Okay. Again, the shape is named a hyperbola. Each piece is called a branch. And we did this based on our knowledge of transformations, plus 2 vertical shift, plus 3 horizontal shift 3 to the left. Okay. All right, so why don't we try problem number 2. If you're watching along at home, please pause the video and try problem number 2. And let's see if you can do it using our knowledge of transformations. All right, so welcome back. Again, looking at this graph, a plus 1 shifts our horizontal asymptote up 1 unit. A minus 2 gives us a horizontal shift of everything 2 units to the right. Again, at this point, we have enough knowledge to talk about the domain and range. The domain will be x is a real number, but x cannot equal 2. And again, you can either look at where the vertical asymptote is, or you can look just at the denominator and say, what value is going to make the denominator 0? That's enough to know. And now the range, y is a real number, but y cannot equal, and we look at the horizontal asymptote here, so y cannot equal 1. Okay. And now to finish off our graph, we know it's going to be in the shape of a hyperbola. It's not a big deal. What we do need to look at is exactly where that happens, so we can make an xy table to help us out with that. So for instance, an x value of 3 gives us 3 over 1, which is 3, plus 1 is 4. An x value, let's try something. I don't know. How about an x value of 5? Gives us 3 divided by 3, which is 1. 1 plus 1 is 2. So 3, 4, 2, 3. There's 3, 4, and 5, 2. 1, 2, 3, 4, 5, 1, 2. And so our graph will look like that. And so we probably get a similar like that. And again, there's got to be a symmetry property between the branches, so you can kind of eyeball it. Otherwise, you can just make a longer xy table. Now, what's nice about this problem, between problem number 2 and problem number 3 here, is problem number 2, you can see the transformations. On problem number 3, you cannot. So it's slightly problematic. So we need another way to be able to address problem number 3, and we have a way to do that, but we need some of this knowledge. Okay. So the vertical asymptote is still created by the value that makes the bottom of the fraction 0. The only thing is, the value that makes the bottom of the fraction 0 is going to get more and more complex, so they kind of give you this structure, negative d over c. That is the value that makes the bottom of the fraction 0. Okay, so it doesn't matter what c is, it doesn't matter what d is, that's the value that's going to make the bottom of the fraction 0. And this you could calculate, and they actually explain how they got this. Look, because the function is undefined when the denominator equals 0. So all they did is they did this. They did cx plus d equals 0, and they solved this, and they found that x equals negative d over c. Okay? This is the value that makes the denominator 0. That's why it's negative d over c. Now, They also tell you how to find the horizontal asymptote. Why that is, we're going to leave that for a different lesson. For now, you just need to know that to calculate the horizontal asymptote, if you cannot see the transformations, let me say that again. To calculate the horizontal asymptote, if you cannot see the transformations, you need to go y equals a over c, and that'll tell you where the horizontal asymptote is. Okay? So here we are. So what value makes the denominator 0? And that's going to be the only value that's not in the domain, and that's also going to be where our vertical asymptote is. So x can't equal 1. Right? That's going to make the denominator 0. And so at x equals 1, we get our vertical asymptote. Now, if we want to talk about the range, we need that previous knowledge from the previous slide that says the range is going to be all real numbers except for 4 divided by 1, a over c. So this is a, this is c, and so y cannot equal 4 divided by 1, which is just 4. And that's going to be where the horizontal asymptote is. 1, 2, 3. 1, 2, 3, 4. Okay. So as we proceed in graphing, we can as soon as we identify the asymptotes, we can identify the domain and the range. And now the only thing we have left to do is to graph this. We come out with our xy table and pick an x value like 2, and we get 8 minus 2 is 6 divided by 1, so this is 2, 6. If we pick an x value like 3, we get 12 minus 2 is 10 divided by 2, so this should be like 3, 5. So 2, 6, 1, 2, 2, 4, 6, 3, 5. So there's part 1. And part 2 is going to look much the same. Okay. Probably more interested in where the asymptotes are than the actual graphs. Remember, your graphing calculators are going to do this for you, so I'm not too worried about the graphing piece, but I need you to see how the asymptotes are calculated and how we talk about domain and range. As we proceed with rational functions, you're going to find out that they won't always have asymptotes. All right, so rational functions are they can create some very unique situations, but in this section, all of them should have 2 asymptotes, both a horizontal and a vertical. And this is going to be the thrust of what we spend our time in Chapter 8 looking at, is these types of functions, rational functions. All right, so one last problem. So why don't we work on this, number 3. And more than graphing it, I want you to be able to tell me where the asymptotes are and what the domain and range is. Okay. So you can pause the video now and please tell me where the asymptotes are, the horizontal and the vertical, and what the domain and the range is. All right, so as we look at this guy on number 3, we see that the domain is going to be all real numbers, so x is a real number, but x cannot equal negative 2. If I plug in negative 2, I don't care what happens in the top. We don't care about what happens at the top. We just look at the bottom. It makes the bottom 0. Therefore, this is not, it's undefined. The function's undefined. So x cannot equal negative 2, and so that's going to give us our asymptote here at x equals negative 2. Okay. And we look at the range. Now to talk about the range, we need to have that previous knowledge from the previous slide that says the horizontal asymptote is going to occur at a over c, which is negative 2 divided by negative 1, which is just positive 2. So y cannot equal positive 2. And that's where the horizontal asymptote would occur. Okay, and that's generally the idea. If you want to see what the graph would look like, roughly the graph is going to do this, right? It's a hyperbola shape. I know it's got to sit in. It's got to push into the asymptotes, right? So as it keeps going in this direction, it's got to get closer and closer to the asymptote. As it pushes into this direction, it's got to get closer and closer to the asymptote, because that's what it means to be an asymptote. All right. Now, it might not curve right here. It may curve closer. It may curve out farther away. You know, it might be something more like this. And that's why you have to do the XY table to try to get that a little bit more accurate. But I'll tell you, as a teacher, I'm looking for where the asymptotes are. That's going to be the primary indicator. If I ask you to graph something, I'm going to look first to see if you put the asymptotes right. And as long as everything else seems reasonable, that's what I'm going to be looking for. Okay? So this is section A2. Thanks for your attention. Have a good day.